Today, Mars is easy to recognize. Even if you've never looked through a telescope, you've probably seen it at some point, a small reddish light drifting among the stars. To most people, it's a desert world, cold, dry, empty, a place where nothing grows and nothing moves except dust carried by the wind. And from a distance, that description seems accurate. Mars is frozen. Its atmosphere is thin. Liquid water cannot survive on its surface for long. Average temperatures can plunge far below anything experienced on Earth. If astronauts landed there tomorrow, they would be stepping into one of the most hostile environments in the solar system. But that version of Mars, the one we know today, is only the ending. And like any ending, it makes much more sense once you know the story that came before it. Because there was a time when Mars looked very different. Not slightly different, fundamentally different. A time when rivers carved their way across its surface, when lakes filled enormous basins, when water flowed beneath open skies. A time when Mars may have possessed something that sounds almost impossible today. A chance, a genuine chance of becoming a living world. If you could travel back more than 4 billion years, the solar system would feel unfamiliar. The planets were younger. The sun was dimmer. Asteroids crossed the inner solar system in huge numbers. Worlds were still forming, still changing, still deciding what they would become. Earth and Mars were not the worlds we recognize today. In some ways, they looked like siblings. Both had rocky surfaces. Both possessed atmospheres. Both had abundant water. Both experienced volcanic activity. Both were shaped by impacts from space. And both may have had environments where life could begin. Yet something happened. Somewhere along the way, their paths separated. Earth became a blue world covered with oceans, forests, ecosystems, and eventually civilizations. Mars became a frozen desert. One world gained a future. The other lost it. And the deeper scientists investigate Mars, the stranger that divergence becomes. Because the evidence suggests Mars wasn't always doomed. It didn't begin as a failed planet. It may have come surprisingly close to becoming another Earth. That idea has transformed the way we study Mars. For decades, scientists searched the planet looking for signs of water. Now they ask a more profound question. What happened? How does a world go from rivers to deserts? From lakes to dust? From possibility to silence? The answer stretches across billions of years. It involves planetary interiors, magnetic fields, climate change, asteroid impacts, atmospheric escape, and perhaps even the earliest chapters of life itself. And in many ways, Mars has become more than a scientific target. It has become a warning, a planetary case study in how worlds evolve and how they die. There's another reason Mars fascinates us. Unlike the distant exoplanets discovered around other stars, Mars is close. Cosmically speaking, it's right next door. Every image sent back by orbiters and rovers reveals landscapes that feel strangely familiar. Ancient river valleys, dried lake beds, sedimentary layers, volcanic plains, canyons larger than entire countries. Sometimes the photographs resemble deserts on Earth. Sometimes they resemble Antarctica. Sometimes they look like places where human beings could almost belong. Almost. That word follows Mars everywhere. Almost habitable. Almost Earth-like. Almost alive. Almost. Perhaps that's why Mars captures our imagination more than any other planet. Because it feels unfinished. Venus became an inferno. The outer planets became giants of gas and ice. But Mars sits in a strange middle ground. Not completely alien. Not completely familiar. A world suspended between what it was and what it might have been. And somewhere beneath its dusty surface, scientists continue searching for clues. Because if Mars once supported life, even microbial life, it would change one of humanity's oldest assumptions. It would mean life emerged twice in the same solar system. Twice, on neighboring worlds. And if that happened here, what might be happening across the galaxy? But before we search for life, before we send astronauts, before we imagine cities beneath Martian domes, we need to go back to the beginning. Back to a time before Mars became the red planet. Back to a young world covered with water, energy, and possibility. Because the story of Mars does not begin with a desert. It begins with an opportunity. One that may have slipped away. If you were somehow able to stand above the solar system 4.5 billion years ago, you wouldn't recognize any of it. There would be no blue Earth, no familiar continents, no forests, no oceans, no Mars as we know it today. The planets existed only as unfinished worlds, still assembling themselves from the leftover debris of the sun's formation. Dust collided with dust. Rock collided with rock. Entire protoplanets crashed into one another. The early solar system wasn't a carefully arranged clockwork mechanism. It was a construction site, violent, chaotic, and constantly changing. For tens of millions of years, growing worlds fought for survival in a crowded neighborhood filled with collisions. Some planets grew large. Others were shattered. Some were thrown entirely out of the solar system. The worlds that survived would eventually become the planets we know today. Earth was one of them. Mars was another. And for a brief period in cosmic history, their futures may have looked surprisingly similar. When scientists study ancient Mars, they often describe it as a smaller version of early Earth. Not identical, but familiar. Both planets formed from roughly the same materials. Both occupied the inner solar system. Both experienced intense volcanic activity. Both possessed atmospheres. And perhaps most importantly, both had water. A lot of water. That last point would have sounded controversial only a few decades ago. For much of modern history, Mars was viewed as a permanently dry world, a cosmic desert that had always been barren. But spacecraft changed that picture completely. Today, the evidence is difficult to ignore. Ancient river valleys stretch across the Martian surface. Deltas sit frozen in time. Sedimentary rocks reveal long interactions with liquid water. Minerals formed in lakes and shallow seas still exist today. Every new mission seems to uncover another clue. Taken together, they tell a remarkable story. Mars was once wet, not occasionally wet, not briefly wet, but persistently wet, for millions of years, and perhaps much longer. Imagine standing on Mars more than 4 billion years ago. The sky wouldn't look like today's dusty salmon-colored haze. Instead, it may have been thicker, darker, filled with clouds. Rain may have fallen. Streams may have flowed across the landscape. Water collected in low regions, carving valleys that remain visible even now. Some of these valleys extend for hundreds of kilometers. They're not random features. They're exactly what geologists would expect to see if liquid water flowed repeatedly across the surface. And that's what makes them so important. Because rivers require more than water. They require time. A single flood can leave scars. A river system leaves a history. Mars appears to have had that history. One of the most compelling examples lies in a region called Jezero Crater. Today it's a dry basin surrounded by dusty terrain. But billions of years ago, it appears to have been a lake, not a temporary puddle. A real lake, fed by rivers that carried sediment from higher elevations. Over time, those sediment accumulated into a delta, the same kind of feature seen where rivers enter lakes and oceans on Earth. When NASA selected Jezero Crater as a landing site for the Perseverance rover, this ancient delta was one of the primary reasons. If microbial life ever existed on Mars, places like this would have been among the best locations for preserving evidence. Not because scientists know life existed there, but because if life had emerged, it would have needed environments like these: stable water, chemical nutrients, energy, time. Ancient Mars appears to have offered all four. This is where the story becomes fascinating, because when we look at early Earth and early Mars side by side, neither world seems obviously destined to win. Today, Earth feels inevitable. Of course, Earth became the living planet. Of course, Mars became the desert. But history rarely feels inevitable while it's happening. For a billion years ago, the outcome wasn't obvious. In fact, some planetary scientists argue that early Mars may have become habitable before Earth stabilized. That idea sounds strange at first. After all, Mars is smaller and farther from the Sun. Yet there are reasons to take it seriously. Earth spent much of its earliest history enduring catastrophic impacts. The most famous of these likely formed the Moon. Meanwhile, Mars appears to have cooled faster. Its surface may have become stable relatively early. For a period of time, Mars may have possessed lakes, rivers, and potentially habitable environments, while Earth was still recovering from enormous planetary-scale collisions. Imagine that. The first truly habitable world in the solar system might not have been Earth. It might have been Mars. Of course, habitability and life are not the same thing. A planet can possess water without possessing biology. That's an important distinction. Scientists still do not know whether life ever emerged on Mars. The evidence remains incomplete. What we do know is that Mars had opportunities, and in science, opportunities matter. Life, as we understand it, requires ingredients: liquid water, complex chemistry, sources of energy, and enough environmental stability for those ingredients to interact over long periods. Ancient Mars appears to have checked many of those boxes, perhaps not all of them, but enough to keep researchers interested decades later. As orbiters mapped the planet in increasing detail, something unexpected happened. The more scientists looked at Mars, the less alien it seemed. Some regions resembled dried river systems found in the American Southwest. Others looked remarkably similar to volcanic landscapes in Iceland. Certain sedimentary formations would not seem out of place on Earth at all. Again and again, Mars presented landscapes that felt familiar, not identical to Earth, but close enough to raise uncomfortable questions. Questions like, what if Mars had remained warm? What if its atmosphere had survived? What if its climate had remained stable for another billion years? Would we be talking about Mars as a second Earth today? Or even as a second cradle of life? These questions don't have easy answers, but they point toward the central mystery of Mars. Because something clearly changed. Dramatically, a world that once supported flowing water became one where liquid water can barely exist on the surface. A planet that once appeared promising became hostile. Somewhere between ancient Mars and modern Mars, the story took a turn, and understanding that turn has become one of the most important goals in planetary science. Because Mars is more than a neighboring planet. It is a natural experiment, a real-world example of how a potentially habitable planet can change over time. In many ways, it offers a glimpse into processes that may be occurring on countless worlds across the galaxy. Every year, astronomers discover new exoplanets orbiting distant stars. Some appear rocky, some occupy habitable zones, some may possess oceans. But we cannot travel to those worlds. Not yet. Mars is different. Mars is close enough to study directly, close enough to explore, close enough to touch. That makes it invaluable. Because hidden beneath its deserts is a record of planetary evolution written across billions of years. A record scientists are still learning how to read. And the deeper they investigate, the more one conclusion becomes difficult to avoid. Mars didn't simply become a desert overnight. Its transformation happened gradually, step by step, layer by layer, a slow unraveling of a world that once seemed full of potential, which raises perhaps the most important question in the entire story. What exactly went wrong? How does a planet lose an atmosphere? How does it lose oceans? How does it lose a future? To answer that, we need to look beneath the surface, deep into the interior of Mars itself. Because the fate of a planet is often decided not by what happens above the ground, but by what happens far below it. When people think about planets becoming uninhabitable, they usually imagine dramatic events. A giant asteroid, a supervolcano, a nearby star exploding, something sudden, something catastrophic, something that happens in a single terrible moment. But the death of Mars wasn't like that. There was no single day when rivers stopped flowing, no final storm, no last sunset over an ancient ocean. If Mars died, it died slowly, so slowly that no living thing, if anything was there to witness it, would have noticed a change happening. Year after year, century after century, million years after million years, the world simply became a little less alive, a little colder, a little drier, until eventually it became the planet we see today. And strangely enough, the beginning of that transformation may have started deep underground, far beneath the valleys, volcanoes, and ancient lake beds, in a place no rover will ever reach. The core. To understand what happened to Mars, we need to talk about something invisible, Something most people never think about, because Earth makes it seem ordinary: the magnetic field. Right now, as you sit watching this video, Earth is surrounded by a vast magnetic shield. You can't see it. You can't touch it. Yet it stretches tens of thousands of kilometers into space, protecting our planet every second of every day. Without it, Earth would be a very different world, perhaps not unlike Mars. The sun doesn't only produce light, it also releases a constant stream of charged particles known as the solar wind. Imagine a river flowing outward in every direction from the sun, a river made of energetic particles moving through space at extraordinary speeds. Every planet in the solar system sits inside that flow, including Earth, including Mars. The difference is that Earth has protection. Mars eventually lost its own. Earth's magnetic field is generated deep inside the planet, beneath the crust, beneath the mantle, inside the molten outer core. There, vast currents of liquid iron move continuously. These motions generate a planetary magnetic field that extends far into space. The process is known as a geodynamo. It's one of the reasons Earth remains habitable today, not because the magnetic field creates life, but because it helps preserve the conditions that allow life to exist. Think of it as a planetary defense system. Not perfect, but incredibly important. Mars once had one too. That fact surprised scientists. Today, Mars has no global magnetic field, only scattered magnetic remnants trapped in ancient rocks. For a long time, researchers weren't sure what this meant. Then spacecraft began measuring the magnetic signatures preserved within the Martian crust, and a remarkable picture started to emerge. Billions of years ago, Mars possessed an active magnetic field, a real one, a global shield, strong enough to protect the atmosphere from the full force of the solar wind, which means early Mars wasn't just wet, it was protected, at least for a while. Something changed, and whatever changed everything. At some point in Mars' early history, the dynamo inside the planet shut down. The exact timing remains debated, but evidence suggests it happened surprisingly early, possibly within the first few 100 million years of the planet's existence. By geological standards, that's incredibly fast, especially compared to Earth, whose magnetic field remains active more than 4 billion years later. The question is why? Why did Earth's engine keep running while Mars' engine stopped? The answer may come down to size. Mars is only about half the diameter of Earth. At first glance, that doesn't sound dramatic, but planetary size affects everything. Larger planets retain heat longer. Smaller planets cool more quickly. And Mars, being significantly smaller, may simply have lost its internal heat faster. Over time, the motions within its core slowed. The dynamo weakened. Then eventually, it stopped. The magnetic shield disappeared. And for the first time, Mars stood exposed. Imagine removing the roof from a house during a storm. The house doesn't vanish immediately. At first, everything seems normal. The furniture remains. The walls stand. Life continues. But little by little, the weather begins to take its toll. Rain enters. Wind causes damage. The structure weakens. Years later, the house no longer resembles what it once was. Something similar may have happened on Mars. The atmosphere didn't disappear overnight, but once the magnetic field was gone, the solar wind gained direct access to the upper atmosphere. And for billions of years, it slowly stripped it away, particle by particle, layer by layer. NASA's MAVEN mission has helped reveal this process in extraordinary detail. Even today, Mars continues losing atmospheric particles to space. Not rapidly, but continuously. The planet is still leaking, still surrendering pieces of its atmosphere to the vacuum beyond. The process is measurable, observable, happening right now, which means Mars isn't simply a dead world. In a sense, it is still dying. The transformation that began billions of years ago has never completely stopped. As the atmosphere thinned, the climate began changing. This is where the story becomes particularly important, because atmosphere and water are deeply connected. On Earth, atmospheric pressure allows liquid water to remain stable on the surface. Take away enough pressure, and liquid water struggles to survive. That's exactly what happened on Mars. As atmospheric pressure declined, surface water became increasingly unstable. Lakes began shrinking. Rivers flowed less frequently. The hydrological cycle weakened. Eventually, much of the remaining water either froze or escaped into space. The world that once supported flowing rivers slowly transformed into a frozen desert, not because water never existed, but because the planet lost the ability to keep it. What's fascinating is that many traces of that ancient world still remain. Orbiters have identified minerals that only form in the presence of water. Ancient shorelines may still exist. Subsurface ice remains widespread. Enormous deposits of frozen water hide beneath the surface. Mars never completely lost its water. It lost its accessible water, its active water, its living water, the kind that shapes landscapes and supports ecosystems. And as conditions worsened, the planet entered a feedback loop. A thinner atmosphere led to cooler temperatures. Cooler temperatures caused more water to freeze. Less water meant fewer climate-stabilizing processes. The environment became increasingly hostile. Each change reinforced the next. The decline accelerated, not dramatically, but relentlessly. What makes this story so compelling is that Mars wasn't destroyed by some extraordinary cosmic disaster. There was no rogue planet, no nearby supernova, no apocalyptic collision. Mars may have been undone by something far simpler. It cooled, its magnetic shield disappeared, and everything else followed. The difference between a potentially habitable world and a frozen desert may have been hidden inside the planet all along. This realization has changed how scientists think about habitability throughout the galaxy, because when astronomers discover Earth-sized exoplanets around distant stars, one question immediately follows. Do they have magnetic fields? Not because magnetic fields guarantee life, but because Mars demonstrated what can happen when one disappears. A planet can have water. A planet can have a promising climate. A planet can have all the right ingredients and still lose everything. Perhaps that's the most haunting part of Mars' story. When we look at the red planet today, we're not seeing a world that never had a chance. We're seeing a world that may have come remarkably close. A world that almost held on to its atmosphere, almost preserved its rivers, almost remained habitable. Almost. And that word continues to follow Mars through every chapter of its history. As the atmosphere faded and temperatures dropped, the transformation accelerated. Ancient lakes vanished. The climate shifted. Dust replaced water. Ice replaced rain. The familiar red desert began to emerge. But even then, Mars still wasn't finished changing, because another force was preparing to reshape the planet. One that would leave behind the largest volcano in the solar system, the largest canyon in the solar system, and scars so vast they can be seen from orbit. The story of Mars was about to become even more dramatic. If Mars once had rivers, if it once had lakes, if it once possessed a thicker atmosphere and a warmer climate, then why does the planet look so different from Earth today? Why does its surface feel so alien? Why does it contain some of the most extreme landscapes anywhere in the solar system? The answer lies in one of the strangest consequences of Mars being a smaller world. Because while Mars may have lost many of the things that made it Earth-like, it gained something else in return. Scale. Extraordinary scale. The kind of scale that forces geologists to rethink what a planet is capable of building. And nowhere is that more obvious than the largest volcano humanity has ever discovered. Imagine standing on the plains of Mars. The horizon stretches endlessly in every direction. The sky glows with a faint reddish haze. Dust drifts across the landscape. And somewhere ahead of you rises a mountain so large that you wouldn't actually recognize it as a mountain. At least not at first. Because Olympus Mons is too big for the human brain to process in a single view. On Earth, when we look at Mount Everest, we can see its shape. Its peak rises dramatically above the surrounding terrain. The mountain feels like an object. Olympus Mons doesn't. It feels like geography itself. Olympus Mons stands roughly 22 kilometers high. That's nearly 3 times taller than Mount Everest when measured from sea level. Its base spans approximately 600 kilometers across. To put that into perspective, you could place entire countries inside its footprint. If Olympus Mons existed on Earth, It would dominate an entire continent. Airline passengers would see it from hundreds of kilometers away. It would fundamentally alter weather patterns around it. It would become one of the defining features of the planet itself. And yet on Mars, it is only one volcano among many. For years, scientists struggled to understand how a volcano could become so enormous. On Earth, volcanoes grow, but they also face limitations. The crust moves, tectonic plates shift, volcanic hotspots drift beneath the surface. As a result, volcanic activity spreads out over time. A single volcano rarely remains above its magma source for millions upon millions of years. Mars appears to have played by different rules. Unlike Earth, Mars does not have active plate tectonics, at least not in the way we experience them. Earth's crust is divided into moving plates that slowly slide across the planet's surface. These movements recycle crust, build mountains, and create oceans. They also prevent volcanoes from growing indefinitely. Mars lacks that constant reshuffling. Its crust remained relatively stationary, which meant that when magma found a pathway to the surface, it could keep erupting in roughly the same location for incredibly long periods. Layer after layer, eruption after eruption, million year after million year. The result was Olympus Mons, a volcano that simply never stopped growing. And Olympus Mons wasn't alone. The surrounding Tharsis region became home to several giant volcanoes: Ascrius Mons, Pavones Mons, Arsia Mons, each enormous, each dwarfing most volcanic structures on Earth. Together they form one of the most impressive volcanic provinces in the solar system. Looking at orbital imagery, the region almost appears unreal, as though someone exaggerated the landscape beyond what geology should allow. Yet the evidence is undeniable. Mars built giants. What's remarkable is that these volcanoes weren't merely shaping the surface. They were influencing the entire planet. Volcanic eruptions released gases into the atmosphere. They altered climate, affected surface chemistry, perhaps even contributed to temporary warming periods during Mars history. Some researchers believe volcanic activity may have helped maintain habitable conditions at certain points in the planet's past. Not permanently, but long enough to matter, long enough to leave traces. Then there is Valles Marineris. If Olympus Mons represents the greatest volcano in the solar system, Valles Marineris may represent its greatest canyon. Calling it a canyon almost feels misleading. The term doesn't capture the scale. Imagine taking the Grand Canyon and stretching it thousands of kilometers across a planet, then making parts of it several times deeper. That's closer to reality. Valles Marineris extends for roughly 4,000 kilometers. If placed on Earth, it would span much of the continental United States. Its deepest sections plunge more than 7 kilometers below the surrounding terrain. From orbit, it appears like a gigantic wound across the face of Mars, a scar visible from space, one of the most dramatic geological features known. For decades, scientists debated how it formed. At first glance, it resembles a gigantic canyon carved by water, but the reality appears more complex. Many researchers now believe Valles Marineris began as a tectonic fracture. The crust stretched, cracked, collapsed, and over time, erosion, landslides, and possibly flowing water modified the structure further. The result is a landscape unlike anything found on Earth. Part canyon, part rift valley, part geological mystery. If you could stand near the edge of Valles Marineris, the view would be overwhelming. The opposite side might disappear beyond the horizon. Sheer cliffs would plunge downward for kilometers. Dust storms would swirl through the depths. Ancient layers of rock would reveal billions of years of planetary history, exposed like pages in a book. Every layer telling part of Mars' story. Every layer preserving clues from a different era. And that's what makes these giant structures so important. They're not merely impressive. They're archives. Olympus Mons records the volcanic history of Mars. Valles Marineris records tectonic and climatic history. Ancient crater basins preserve evidence of water. Polar ice caps preserve environmental changes. The entire planet functions as a geological time capsule. Unlike Earth, where plate tectonics continuously erase ancient evidence, Mars preserved much of its early history. In some regions, scientists can study surfaces that are billions of years old. landscapes that have survived almost unchanged since the earliest chapters of the solar system. This is one reason planetary scientists love Mars, not because it is alive, but because it remembers. Earth is dynamic, active, constantly rewriting its own history. Mars is different. Mars keeps old records. Its deserts preserve stories that Earth lost long ago. Stories about planetary formation, atmospheric collapse, volcanism, water, and perhaps even life. In a strange way, Mars may be the better historian. Earth is the living planet. Mars is the archive. And sometimes archives are exactly what scientists need. Because if we want to understand how planets evolve, how climates change, and how habitability begins or ends, Mars offers lessons that Earth no longer can. But among all these giant volcanoes and colossal canyons, one mystery continues to overshadow everything else. Because beneath the dust, beneath the ancient lake beds, beneath the volcanic plains, lies a question that has haunted generations of scientists. A question that grows more intriguing with every mission. What if Mars wasn't merely habitable? What if something actually lived there? Not cities, not civilizations, not intelligent beings. Something much smaller, much older, yet potentially far more important. Because discovering even the simplest life on Mars would transform our understanding of the universe forever.